If you think you understand the Earth's weather, you are probably wrong. Everyone knows our climate is changeable. Its temperature, its rain, its winds, and its tides seem to shift all the time with so little rhythm or reason that not even the weathermen can keep up. But that just goes to show how vastly complicated the systems are that govern the Earth's climate. There are so many cycles at play, it can seem impossible to understand exactly why our skies, winds, and tides behave in the way that they do on any given day. This is particularly relevant when you hear so many voices that argue for or against humanity's impact on the weather we're experiencing. Some seem vehemently opposed to the idea that we have significantly influenced our own climate. Others treat it as an absolute certainty. Where does the truth lie? If you'll forgive my pun, it's time to clear the air. From Milankovitch cycles to atmospheric wind patterns, the influence of the sun or the moon, to movements deep within the Earth's fiery core. We're going to discuss it all. It all makes a difference. I'm Alex McColgan, and you're listening to the Astrum podcast. And in today's compilation episode on Earth cycles, we're going to unravel exactly why the weather is the way it is today. And most importantly, whether our climate is shaped the most by something we can see outside the window or in the mirror. Let's start with some big picture thinking. If we're going to understand our global climate, we need to start by thinking about our place in the solar system. What causes the seasons that we are familiar with? You may well already know the answer to this question, but as it will provide the starting point for what comes later, it's worth reviewing. Besides, this question is not entirely straightforward. Depending on where you are on the planet, you may not actually get any seasons. Generally speaking, seasons we know of are caused as a result of our planet's tilt. Because our planet rotates at a tilted angle as it orbits the sun, one hemisphere will point towards the sun during part of the year, while the other will point away. Naturally, hemispheres that are pointed towards the sun become much warmer, while pointing away from the sun makes them colder, creating the regular seasons, summer and winter. This effect becomes stronger the higher up or lower down the planet you go. Consider the small Norwegian town of Tromsø. Because of its higher altitude, Tromsø isn't just pointed more towards the sun. The tilt of the Earth is such that from its perspective, the sun never sets for months in summer and never rises for a few months in winter. Naturally, this produces quite the seasonal variance. But this effect lessens the closer to the equator you get. There, the tilt of the Earth doesn't really change the angle at which the sunlight strikes the ground, and as such, the Earth doesn't notice much temperature variation. It's all just a question of angles. Is sunlight hitting the ground dead on, allowing its rays to be at their most concentrated? Or are they hitting at an angle where the number of rays are smeared over a larger area, diluting their overall power? The answer to that question can make a big difference on the temperature, which is a big part of why the Arctic is so much colder than the equator. However, did you know that the tilt of the Earth isn't static? Nor is it the only thing about a planet's orbit that influences how warm or cold we are. Imagine for a second the model you are familiar with, of the Earth orbiting the Sun in a nice circle, flat to the plane of the solar system. In this model, we circle the Sun because of the Sun's gravity. This model is too basic. In reality, the Sun is not the only source of gravity pulling at us, although it is the biggest. Many of the planets pull and tug at us, particularly large ones like Jupiter, which has a mass 318 times the size of our own planet, or Saturn, which is 95 times. And we, in turn, pull on them. As planets all rotate at different speeds around the Sun, this constant pulling and releasing creates a delicate dance, far more complicated than a simple circle. This interplay of increasing and lessening gravity has many different effects on our angle of tilt, our orbit, and even the plane in which they occur. Broadly speaking, these variables have stabilized into cycles. These cycles were first described effectively by Serbian geophysicist and astronomer Milutin Milankovitch in 1920, and thus were called Milankovitch cycles. The first such cycle I want to look at is the changing shape of our orbit. Over the course of a 100,000-year period, the Earth's orbit around the Sun becomes more and then less elliptical. Naturally, if our orbit is closer to that of a circle, our distance from the Sun remains relatively consistent, and we get about the same amount of sunlight all year round. However, once our orbit becomes elliptical, there are parts of the year where we are further from the Sun and thus colder, and parts where we're closer and warmer. As it happens, the perihelion of the Earth's orbit, or the bit where we're closest to the Sun, happens roughly on January 3rd, while the aphelion, or the bit where we're furthest away, happens on roughly July 4th. I'm recording this in the UK, which means for my hemisphere, January is winter. So for me, this is quite nice. Although we are in a phase right now where this cycle of the Earth's orbit is more circular than it is elliptical, we still experience a 7% difference in the amount of sunlight we receive in January compared to July. This sunlight difference means that my northern hemisphere's winters are warmer, while our summers are milder. In the southern hemisphere, the reverse is true. Because they're experiencing summer during this warmer phase, their summers become even warmer, winters become colder. And that's just at this stage of the 100,000-year Milankovitch cycle. As the Earth's orbit becomes more elliptical, that 7% sunlight difference turns into a 23% difference. Quite significant. You might think this seems overall a little unfair on the southern hemisphere. The northern hemisphere benefits from this cycle stabilizing its seasons, while this cycle makes the southern hemisphere's seasons more extreme. Don't worry though, as another cycle is at play to bring things full circle. This current seasonal rotation happens because the Earth's tilt is consistent as it orbits, except it isn't consistent. Little by little, the angle the Earth's axis is rotating along is changing too. It moves as if it were drawing a circle on the sky above it, in a cycle that lasts 26,000 years. One upshot of this is that while our axis is currently pointing at the North Star, or Polaris, this will eventually no longer be the case. Over time, it will point at different stars, before eventually circling back to point at Polaris again. The other upshot of this is that in 13,000 years, the Northern Hemisphere will be having its summer in January, while the Southern Hemisphere will be the one with a white Christmas. So, then it will be us experiencing a more profound seasonal variation. While harsher winters are unpleasant, at least they go away after a few months. This is nothing. There are Milankovitch cycles that create winters that last for thousands of years. Or, to speak more accurately, there are Milankovitch cycles that help cause ice ages. We don't fully understand how ice ages come and go. There are numerous theories. However, it must be noted that some of the 100,000-year spans of ice ages line up extremely well with the 100,000-year Milankovitch cycles. For instance, there is a cycle whereby the plane on which the Earth rotates around the Sun rises and falls over the course of 100,000 years. This change in its orbital inclination does not obviously explain why it is that the Earth would be getting colder or warmer. After all, the Earth is still the same distance from the Sun. However, it lines up so perfectly with the time periods ice ages were occurring at over the last 800,000 years that scientists conclude that there must be a connection. Perhaps cosmic dust lying in the plane of Earth's orbit blocks out some sunlight when we are at one inclination, but is not in the way when we are at another. This could go some way toward explaining the occurrence of ice ages during these time periods. Whatever the case, there is at least one other cycle that influences the arrival of ice ages on Earth, and this might perhaps be the most important for us today. It is the tilt of Earth's rotation. I already mentioned that this axis of tilt rotates around the planet, but it also changes the angle at which it does this. Over the course of 41,000 years, it alternates between 22.1 degrees and 24.5 degrees. At the moment, it is 23.4 degrees and is declining. You might think that this is a good thing. The smaller the angle of tilt, the less extreme our seasonal temperature variations might be, and the warmer our winters will become. Surely that is a good thing for avoiding ice ages. Surprisingly, it is quite the opposite. Left to its own devices, this lessening tilt would lead us into another spreading of the ice sheets and cooling of the planet that would hit its peak in 9,800 years. It is not the harshness of the winter that causes this spread, but strangely enough, it is the mildness of the summers. You see, when winters occur, snow builds up at the top of mountains and in cold polar regions. In warm summers, this snow tends to melt away. However, if the summer is mild enough, the snow sticks around, becoming a more permanent feature of the landscape. Icy snow is white in color and reflective, which means that light has a tendency to bounce off it rather than be absorbed by it. This means that if the Earth is covered with ice, it reflects sunlight back into space and actively becomes even colder, thus creating conditions for even more ice. In more than one sense of the word, this is a snowball effect. We are right now in an interglacial period. This is a brief moment of warmth that lasts a few tens of thousands of years or so, interspersing a deeper, more general cold trend. If it wasn't for this warmer uptick, we would actually be in an ice age right now. And from a technical perspective, actually are in an ice age, just one we're not fully noticing. If it wasn't for this briefly warm interglacial period, mankind would have experienced ice across the history of its entire existence. Thanks to the Milankovitch cycles, that brief period of warmth will someday end. Then winter will truly come. Of course, this is under the assumption that Milankovitch cycles are the only factors that influence global temperatures. And while broad trends lasting 100,000 years and interspersing upticks every 41,000 years are indeed demonstrable and consistent in parts of fossil record, the location and orientation of our planet are not the only thing that matters. CO2 and methane levels in the atmosphere are also driving forces behind global temperature fluctuations. And if we're not careful, just as an ice age can build up with a snowball effect, stripping away of ice can happen in the same way, but in reverse. Less ice means less reflection of sunlight, making things overall warmer, which leads to less ice. Still, if Milankovitch cycles are the only factor in action, we are in for a cold future. The Milankovitch cycles affecting the planet currently are mostly working to stabilize the system, leaving us in a temperate, relatively even temperature zone. However, there will come a time when they will make temperatures, hot and cold, more extreme. We would do well to keep these cycles in mind. Milankovitch cycles are in it for the long haul.
Winter is coming, as they say in Game of Thrones. It might not be coming for a long time, but one day our planet will face winter again.
Life on Earth is full of cyclical variations. We have day and night, the changing of the seasons, and the ebb and flow of the tides. Many of these changes happen over relatively short periods and can be predicted with precision. But other cycles affect our planet over large intervals and can be trickier to forecast.
Milankovitch cycles play a role in the occurrence of ice ages interrupted by warming intervals.
But given the vast timeline, it's unlikely our own lives will be very affected by them. Yet, there is one climate cycle that definitely will affect you: the El Niño Southern Oscillation, better known as El Nino and La Nina. While El Nino and La Nina originate in the Pacific Ocean, their impacts are felt nearly everywhere on Earth, and by some accounts, the strongest effects are getting more common. In the last few decades, some of the destructive consequences have included flooding, drought, famine, and mass die-offs of marine life. Indeed, a severe El Nino in 1998 caused an estimated 16% of the world's coral reefs to die, kicking off a cataclysmic mass bleaching event that persists to this day. The ENSO is global and will, without a doubt, impact you. So what are El Nino and La Nina? Why are they linked? and what are their global impacts? In our second stop on our tour of Earth cycles, it's time to find out. If you think the name El Nino sounds more like a folk story than a scientific phenomenon, you're onto something. During the 17th century, fishermen noticed periods of warmer water and poor fishing that would peak around Christmas time. They called it El Nino de la Navidad, which means the boy of the Nativity, or the Christmas child. It wasn't until the late 19th and early 20th centuries that scientists began to connect a variety of seemingly disconnected regional events scattered across the planet. By the mid-20th century, they found that these weren't regional occurrences, but phases of a global, cyclical phenomenon called the El Nino Southern Oscillation. The ENSO fluctuates with an average interval of 5 years, although the cycle can take anywhere between 2 and 7 years. We've now been tracking these cycles for decades, but they've been around for much longer than that. To understand why the El Nino Southern Oscillation occurs, let's first look at what happens in the Pacific Ocean under normal conditions. Winds blow along the equator from east to west. This is a product of the Coriolis effect, caused by the Earth's rotation. Here's a fun fact: if the Earth didn't rotate, air would circulate north to south, from the high pressure poles to the warmer, low pressure region at the equator. As it happens, air does circulate off the poles, but it bends as it approaches the equator. In a circumferential band that extends 30 degrees north and south of the equator, sometimes known as the horse latitudes, air in the northern hemisphere deflects to the southwest, and air in the southern hemisphere deflects to the northwest. This channel of westward moving air is called the trade winds. It turns out they're not just important if you're a pirate living in the 18th century. As the trade winds blow westerly across the Pacific Ocean, they drag warm water from coastal South America toward Asia. And as this warm water moves west, colder water rises to replace it, a phenomenon called upwelling. This cold water is rich in nutrients that feed phytoplankton, which in turn support ecosystems of fish and everything that feeds off them. So, as you can imagine, a shock to this system would have a major domino effect on marine life. If this is what normal conditions look like in the Pacific Ocean, think of El Nino as a disruption of normal. During El Nino, the trade winds weaken. As they slow down, warm water that would be flowing toward Asia builds up instead near the coastal Americas, resulting in less upwelling cold water. This, in turn, creates a zone of warm air and water further east in the Pacific. With less upwelling, the fish that feed off the phytoplankton migrate or die. The Pacific jet stream that crosses North America moves south from where it normally occurs. As a result, the northern United States and Canada tend to become warmer and drier, whereas the Gulf Coast and parts of the coastal South America become wetter. Peru and Ecuador receive their wettest months from April to October, and during more severe El Nino years, rain and flooding in those regions can be catastrophic. In the severe El Nino of 1997 to 1998, devastating floods bombarded Peru, collapsing bridges and burying entire shanty towns under a meter-thick layer of mud. In total, 250,000 people were displaced from their homes. The region of Tumbes, which is normally arid, received an unbelievable 16 times its average annual rainfall. Outside the Americas, El Nino sets off a series of domino effects that significantly alters weather worldwide. The increased rainfall in South America typically coincides with a pronounced period of drought in South Asia and Australia. Severe famines have been recorded in India, and a delay in Australia's monsoon season can lead to massively destructive bushfires. Due to its vast expanses of grassland, Australia's bushfires are some of the most destructive on Earth, and there are already concerns about an event that could occur late in 2023. Leaders are understandably worried given recent warming trends. You may remember that in 2020,
in a non-El Nino year, bushfires wrought nightmarishly apocalyptic scenes that left 50 million acres of land charred to a crisp. Australia is a literal tinderbox over which El Nino looms like a proverbial flamethrower, so local officials are wise to prepare for the worst. On a global scale, the average surface temperature during El Nino rises 0.1 degrees Celsius. But not all El Nino events are severe. Some can be rather mild, something to keep in mind before you hit the panic button. The average El Nino lasts from 9 to 12 months, but on rare occasions they have lasted for years. The world's climate is a pretty complex system responding to a number of inputs, so the effects of El Nino are best understood as relative to what the baseline would be, which is why no two El Nino years are alike. La Nina is the opposite side of the El Nino Southern Oscillation. If El Nino is a hot event, then La Nina is a cool one, although some regions do experience warming. As I mentioned earlier, El Nino occurs when the equatorial trade winds slacken, but during La Nina, the trade winds become even stronger. Think of El Nino as a disruption of normal and La Nina as normal plus. The trade winds blow even more warm water from coastal South America toward Asia, resulting in more upwelling of cold, nutrient-rich water near the Americas. For fisheries, this can produce a feeding frenzy. And if you like salmon, well, you're in luck. During La Nina, cold water species like salmon will venture into typically warmer waters where they can't ordinarily survive. The same is also true of squid, in case you prefer calamari. Meanwhile, in Asia, the influx of warm equatorial water produces wet conditions, the opposite of the drought experienced during El Nino, causing a spike in tropical cyclones. In North America, the jet stream is pushed further north. This causes drought in the southwestern United States and rains in the Pacific Northwest. In 2022, La Nina exacerbated a mega drought in the southwest United States, making it the worst in 1,200 years. Now, with all this talk of trade winds and jet streams, you might be wondering how La Nina affects hurricane season. Well, depending on where you live, the news is either good or bad. The Atlantic often experiences a much more severe hurricane season during La Nina because the shift in the jet stream produces greater atmospheric instability in the southern Atlantic. But the Pacific Basin actually sees fewer hurricanes, a sign of how drastically different these regional effects can be. Just don't get too complacent, Pacific dwellers. El Nino has the opposite effect as La Nina. Meanwhile, in Pacific coastal South America, you won't see the warm Christmas-time waters that once prompted fishermen to dub it El Niño de la Navidad. Indeed, there's a reason why fishermen once called La Nina El Viejo, or the Old Man. During La Nina, the weather in Peru and Chile turns colder and drier, sometimes producing severe periods of drought. Brazil's north, on the other hand, becomes wetter during the months from December to February, and the lowlands of Bolivia can receive catastrophic flooding. In Africa, the conditions in La Nina years are basically the reverse of what they are during El Nino. East Africa tends to experience drier than average conditions, whereas the south tends to be wetter than average.
So where are we now in the ENSO cycle?
As of October 2024, the National Oceanic and Atmospheric Administration, or NOAA, has reported that our most recent El Nino has just ended. They concluded this based on measuring the difference in surface atmospheric pressure in the East Central Tropic Pacific, a metric known as the Oceanic Nino Index. Heading for us now is likely La Nina, which is being predicted with a 71% accuracy. However, initial reports indicate that this is going to be a weak event, which is a shame. La Nina's global cooling effect would be a good countermeasure to the ever-increasing global average temperatures we've been seeing lately. For me, this is an excellent example of how studying climate cycles can help us prepare and foster human survival, not just on this world, but potentially on other worlds too. Because one of the fascinating aspects of the ENSO is the level of insight we gain from it into Earth's complex climate systems. Understanding the interconnectivity of our own planet's climate will be crucial if we ever want to settle on other planets or even terraform. If humans eventually undertake the huge task of terraforming Mars, Mercury, Venus, or the Moon, or perhaps even an exoplanet in some other part of the Milky Way galaxy, our success will likely depend on our ability to understand the various inputs and feedback loops that intricately interlink climate systems and biospheres. That day may seem far off, but it isn't too early to start dreaming.
If there's one thing El Nino shows us, it's that the winds of our planet work under vast cycles that ebb and flow over the course of years. However, El Nino is not the only example of this.
If earlier in this podcast you appreciated my Game of Thrones reference,
Winter is coming, you may appreciate that this is a reference that keeps on giving. In a Game of Thrones,
the armies of the Night King in the north are trapped behind a giant wall. Just like in the TV show, it turns out that on Earth there exists a powerful, icy force to the north that is seeking to overthrow its bounds and rush southward. That powerful winter is also kept at bay by a mighty wall, one that allows the nations to the south to enjoy relatively tranquil conditions. And just like in the TV show, that wall eventually gets breached in a wave of ice that sweeps down and threatens the lives of all those in its way. You might not recognize what I'm talking about. Where is this wall? And what is the icy winter it protects us from? The answer to the first question is a name that I find particularly cool: the polar night jet. And it turns out that the polar vortex it protects us from is a biting chill not to be underestimated. What is the polar vortex, and how does the polar night jet protect us from it?
For our third Earth cycle, it's time to take a look at the Earth's atmospheric winds in greater detail. I was a little misleading earlier when I talked about a polar vortex.
There are actually two polar vortexes, one at each pole of the planet. And even there, each vortex comes in two parts: a tropospheric polar vortex, spinning in the section of the atmosphere known as the troposphere, from ground level up to about 10 to 15 kilometers. This is where 75% of the total mass of the atmosphere resides. Above that lies the stratospheric polar vortex, a technically separate weather phenomenon that has its own size, seasonal cycle, and influence on the global climate. Each of these massive cyclones sits over the pole, spinning with the planet's rotation, with wind speeds that can reach up to 240 kilometers per hour. Why do these winds happen? The first piece of the puzzle is temperature difference. At locations like the equator, where sunlight is most concentrated, the air is warmed and starts to rise. As it does so, it creates an area of low pressure beneath it that draws air into it from its surroundings like a giant vacuum cleaner. Meanwhile, at places like the poles, where it's much colder, air contracts and falls, creating zones of high pressure where air molecules want to spread out like a crowd of school children being released into an open field. So naturally, with these two forces at play, there is a tendency for air to rush from the poles towards the equator. Freezing cold winds are constantly trying to escape from the north and south poles. This model is a little simplified though, as wind does not travel in one continuous line from the pole to the equator. Instead, because air from the equator cools and falls much sooner than the pole at around latitude 30 degrees, and air from the poles warms and rises much sooner than the equator at latitude 60 degrees, there are 3 cells of air on each hemisphere that air circulates in. The polar cells, the air masses above the poles, and the Hadley cells, the air masses above the equator, both cycle in the temperature-driven way I described. However, the middle cell, known as the ferrule cell, is not temperature-driven. Like a gear, it is dragged by the rotation of the other 2 cells and rotates opposite to their motion. In terms of our northern polar vortex,
This means that once the air from the pole heads south, it's met by warmer wind traveling in the opposite direction. And when two air fronts of different temperatures meet, they clash rather than mix. So the polar vortex is trapped, bounded, clashing against winds coming in from all sides. There's more at play here though. If this was on its own, the cold air from the north would just slide underneath the warm air from the south, not really being trapped at all. There is a second force at play that redirects those winds, spinning them into a vortex that keeps them circling the poles rather than coming down towards the equator. Where does this spin come from? It's due to something known as the Coriolis force. In a simple, flat world, cold wind from the poles would travel towards the equator, while warm wind from the equator would float over it towards the poles. But the world isn't a simple flat sheet. It's a rotating sphere. You are traveling right now at somewhere between 0 km per hour, if you're at a pole and decided to listen to an Astrum podcast while you were there, and 1,600 km per hour at the equator, from the west to the east. You might not notice this fact because everything next to you is, on average, traveling at the same speed in the same direction. But what happens if you were to travel from the equator to the pole? Conservation of momentum states that you would still be traveling eastward at the same speed as previously, but suddenly the Earth beneath you is not traveling quite so fast. Remember, at the pole you'd have 0 eastward speed, but would simply be rotated slowly. If, on the other hand, you keep all your eastward momentum from the equator and travel towards the pole, suddenly it will appear, compared to everything else, like you are traveling east really fast. In practice, this means that air that travels up towards a pole from the equator, whether towards the North Pole or the South, will not go straight up, but over large distances will start to curve towards the east. This rapidly eastward traveling air is why you get jet streams. There are at least 4 of these, straddling the gaps between the Hadley cells, the Ferrel cells, and the polar cells. The subtropical jet stream lies between the first 2 and is a little weaker, but the jet streams we are interested in are the polar jet streams, wringing the frigid air off that develops in the North and South poles. These ribbons of air circle the globe in an almost continuous path, a little underneath the boundary between the troposphere and the stratosphere. They are only a few kilometers deep, but can be hundreds of kilometers wide, and in their hearts, the wind can travel at 400 kilometers per hour. As a reminder, over 120 kilometers per hour is getting into strength level of hurricanes. The jet stream around the South Pole is fairly stable. Its powerful winds overrule the polar winds trying to leave the polar air mass, whipping them along with it and dragging the entire polar cell into a massive Antarctica-spanning vortex. At this point, a keen-eyed observer might have noticed a flaw in this model. If conservation of momentum means that air going from the equator towards the pole veers towards the east, why is it that air traveling from the pole towards the equator doesn't do the exact opposite? It has 0 momentum, moving to zones that have considerably more momentum. Comparatively, it should be quickly left behind, appearing to start spinning to the west. This is true, but cold winds have much more friction to contend with as it starts to slide underneath the warm front and then drags along the ground. This seems to slow it down enough that the countervailing jet stream overrules it. It's important to note this tension at play though, as it becomes much more important in the polar night jet. The polar night jet is the jet stream that bounds the vortex at the North Pole. Specifically, it bounds the stratospheric polar vortex, keeping it in check during the coldest part of the year for the North, the polar night. Here, during the winter months, the sun is absent from the sky entirely, creating even more freezing temperatures. Interestingly, this colder climate creates a deeper pressure difference between the air around the pole and the air further south, which actually strengthens the force that creates the polar night jet, meaning that during the coldest part of the year, this freezing air is usually well contained. However, this does not always hold true. There are things that can disrupt a jet stream. There are certain zones, such as the boundary between sea and land, or the presence of a large mountain, that can cause disruption to wind. Coastal environments create their own winds that can suck in jet streams, while mountains force an air current to move around it. Even other weather phenomena, such as El Nino, can have an impact on the path the jet stream takes. As the jet stream is not fixed down, but is a balancing point between a range of opposing forces, hitting such obstacles causes it to deviate from its course, and once it starts deviating, it will rock back and forth like a string that has begun bouncing. It shifts, no longer in its balance, overcorrects itself, and is no longer in balance again, and overcorrects itself again, in massive planetary waves that cause the polar night jet to meander around the Earth rather than travel in a straight line, and these oscillations can reach a point where there is a breach. The first sign of this comes in the form of a sudden stratospheric warming, most common in late winter. An SSW can even represent a time where temperatures rise in the polar region by as much as 50 degrees Celsius over the course of just a few days. Something within the system of the jet stream can be so thrown by this that it leads to the southern moving westerly winds overpowering the jet stream, partially or completely reversing its flow. No longer contained, Arctic wind moves south and meets warmer and warmer air, and pushes faster and faster south in an attempt to balance the gradient. The entire jet stream buckles, and suddenly it pivots. It massively reorients itself, traveling down the planet so that regions like Europe and America, usually safely on the warm, temperate side of the polar night jet, suddenly find themselves in the domain of the polar vortex. The forces of winter have arrived. You may not have realized, but one of these jet stream reversals took place just in March 2024. It was a significant reversal too, with wind speeds flowing so fast in the wrong direction, it was labeled one of the top 6 most extreme reversals on record. However, by a stroke of luck, the polar night jet did not meander much from its course in this particular reversal, meaning we did not see the freezing polar winds reaching far beyond their usual Arctic home. Instead, the winds sucked up a large amount of ozone from lower latitudes, causing a spike in ozone above the North Pole, much preferable to an ozone hole. The reversal has already gone back to normal, only flowing in the opposite direction for a couple of weeks. All in all, it could have been a lot worse. In fairness, not all of these events are devastating. With sufficient preparation, you can simply put on some warm clothes, or try to avoid going outside for the month or so that the polar winds are overhead. As long as you're ready for cold, it's not the end of the world. However, sometimes the outcome is serious. In the UK, in 2009 to 2010, the Big Freeze saw parts of Scotland reaching temperatures as low as minus 22 degrees Celsius, the coldest in nearly 40 years, with widespread transport disruption, event closures, and power failures. Sadly, this in turn led to the death of 25 people. In the US, the 2019 January-February North American cold wave saw a polar vortex move down across much of the country with similar outcomes. Some areas saw temperatures as low as minus 50 degrees Celsius, if you take into account wind chill factor from the blustery, freezing winds. Snowstorms raged. You could get frostbite from being outside in just 10 minutes. Sadly, another 22 people died, with hundreds more needing frostbite treatment. Responsible was the ranging polar vortex. In time, the imbalances in the global temperatures restore themselves, and the jet stream returns to its previous position. However, it's worth noting that some level of jet stream breakdown occurs in the north 6 times every decade. If you live in the northern hemisphere, you will likely see many more of these events over the course of your lifetime, although hopefully
not all as powerful as these two examples.
In the south, you are likely safer. There have only ever been 2 instances in recorded history of the southern polar jet stream breaking down in the same way as the northern one.
It has happened though, and the mechanisms behind it are not fully understood. It's difficult to say, as global temperatures gradually rise, what influence this might have on the jet streams. Some evidence indicates that they are traveling further poleward on average year on year, although this is apparently not unheard of in the planet's history. There is some more evidence that the jet streams have strengthened since 2002. If so, we should be grateful. Although unpleasant, the biting cold of the polar vortex usually is only a passing weather phenomenon. We see it return north within a month. But if the jet stream were to go, the polar vortex would come down from the north to stay, and we'd truly know what it is like to live in Arctic conditions. The more I've learned about this subject, the more I've discovered that the winds of our planet are this fascinating weave of interplaying forces and effects that tug and pull on each other, finding perfect balances and yet constantly shifting in rhythms and patterns. And yet, it does so practically invisibly. So much is going on that we simply do not see down here on the ground, just because air is, well, air. And yet, I've learned its importance. The polar night jet is not just wind with a cool name. It is a bastion of protection, a wall against the frozen wind. It really makes you think of the incredible majesty of the world around us, how much is going on that protects us that we simply do not see.
Milankovitch cycles and cycles in our wind can have a slow yet powerful influence on the climate of the Earth, but they are not the only patterns and rhythms shaping the lives of organisms on this planet. For our 4th Earth cycle, let's now turn to one which, rather than originating in the gravitational push and pull between planets and our sun, or the gusting of trade winds, instead lies in the beating heart of magma beneath the Earth's surface. A metaphorical giant hourglass lies deep within our planet that runs out its sands until it's ready for a dramatic reversal. And when those reversals come, the results are devastating to the magnetic fields that keep us safe. And that can be a big problem. It may surprise you to learn this, but the time will come when the North and South poles will swap places. Humanity will need to be ready for the upheaval to our civilization that could follow.
When you think about the North Pole, you don't expect it to go anywhere. And you certainly don't expect it to change places with the South Pole. That would just be wrong. Our magnetic compasses would all point the wrong way. We'd need to update our maps. Birds would probably be horribly confused. And yet, although they sound like something out of science fiction, geomagnetic reversals like this are real. They've happened before, and the process behind it might be a lot more dangerous than you'd think. To be clear, it's not the reversals themselves that are potentially dangerous, it's the buildup. During those times, the Earth's magnetic field, the shield around our planet that keeps us safe from deadly solar radiation, will drop to as low as 10% of its current strength, leading one group of scientists in 2021 to predict climate shifts and mass extinctions, and others to describe satellites being destroyed, electrical grids going offline, and deadly radiation raining down on us for hundreds or even thousands of years. This is troubling when you consider that we are a couple of 100,000 years overdue for our next geomagnetic reversal. And based on fluctuations in the Earth's magnetic field that scientists are detecting right now, the build-up to a geomagnetic reversal may even have begun already. Which begs the question, should we be worried? Let's start by trying to understand where the Earth's magnetic field comes from in the first place. It's not a given that our planet would have a magnetic field. The 2 planets flanking us, Mars and Venus, do not have one, and yet the Earth does, which is a good thing, as without one, there is a very real chance life would not have been able to arise here in the first place. Thanks to the protective cocoon of this field, deadly solar radiation is deflected away from the planet's surface, allowing things to flourish without all that radiation breaking down our DNA, causing mutations and cancers. Scientists are still trying to figure out all the particulars of why certain planets have fields and certain others don't, but the current leading theory is that the Earth's core acts as a giant dynamo. It's a principle of physics that you can use electrical fields to create magnetic ones, and vice versa. This is the principle that power plants work under. Moving a magnet through a coil of wires causes electrical current to start to flow, as that changing magnetic field exerts a force on the electrons present there. But similarly, the motion of electrons creates a magnetic field to form in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate, complicated process. To start with, our core needs to be at least partially liquid, which fortunately is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core, where the pressure isn't quite high enough to keep things in a solid state. It's very hot in the outer core though, 6,000 degrees Celsius at its warmest point, so hot that it rivals the surface temperature of the Sun, which, when combined with the lower pressure compared to the inner core, is more than enough to keep the iron and nickel that makes it up flowing down there. The temperature drops as you move away from the center of the Earth. This gets circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises, then cools, then falls again, creating loops and currents of flowing material. Our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be all over the place. Well, there is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is thought to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to gently be spun in turn, creating giant springs. As each segment of each spring is creating a magnetic field in a circle around it, the net result is that the inside of these springs creates a solid, unified field that all moves in the same direction upwards, while the outside brings that magnetic field looping back down again and back in to the bottom of the coil. In short, it creates the well-known magnetic dipole north and south that we see today. However, if there's anything that you should take away from this, it's that this process is precarious, as it is based on a lot of liquid iron essentially just sloshing around, which is not very consistent. Our magnetic field thus has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has gradually shifted about 1,100 kilometers, leaving its original location in Canada and moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, a big jump. This might still be akin to just the momentary wobbles of a spinning top though. Yes, it deviates somewhat, but it always remains roughly upright. That's a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know? The answer lies locked in our Earth's surface iron. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. However, scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation? The entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have only got 300,000 year gaps between them. Comparatively, it's been 750,000 years since the last reversal. You might think that we're overdue for one, and some have made that claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous period, and it lasted 40 million years. The record holder, the Kierman reverse superchron, was 312 to 262 million years ago, 50 million years with no reversal. Scientists are still trying to understand what causes these flips. However, the current theory is that something, perhaps some interplay between the mantle and the outer core, causes a fluctuation in the core spinning. This disrupts the spiraling shapes of the core's flow, breaking them down. The magnetic field of the Earth stops being unified and generally becomes a sprawling mess, fighting against itself. Several poles might temporarily arise during this period of shifting magnetic confusion. While in time things settle down and the spirals reassert themselves, it seems random as to which way they will do this, meaning about half the time our magnetic North Pole reappears over the geographical South. This reasserting can take 1,000 to 10,000 years. Alright, but would that really be the end of the world? Why does this matter? Well, during that period before the poles reassert themselves, our Earth's magnetic field drops to as low as 10% of its current strength. In theory, this could leave us much more vulnerable to all the solar radiation space throws at us. We could see auroras reaching much further south during that time. Skin cancer rates would increase. Our satellites would find themselves with not enough shielding. Radiation would fry their circuits, causing them to malfunction, shut down, and potentially even slowly fall from orbit. Our electrical grid would be much more vulnerable to solar storms, which could lead to large segments of the Earth's population without power. With no electricity or satellite communication, it would be a devastating blow to our global civilization. It could be worse than that. A research team from the University of New South Wales in Sydney even linked one of the most recent weakenings of the magnetic field, the Lachamps event, a temporary 800-year wobble rather than a full flip, to megafaunal mass extinctions in Australia, including the deaths of Diprotodon, giant Australian wombats, and Procoptodon goliath, giant kangaroos. Temporary wobbles like this are known as geomagnetic excursions rather than full reversals, and they happen over much shorter time frames. Their transition periods can last as little as 200 years rather than 10,000, which can be much more difficult for species to adapt to. In their 2021 study, they argued that there was a spike in atmospheric radiocarbon levels caused by the collapse of the Earth's magnetic field, indicating climate shifts that could have led to these extinctions. The timing lines up uncomfortably. But how real are these risks? Honestly, it's a mixed bag. A point in our favor is that other than this recent study, there is no indication that magnetic field reversals have ever coincided with mass extinction events. It seems like many reversals have come and gone without affecting animal or plant life at all. And even in this study, such mass extinctions seem to have been limited in scope. There is no claim from the researchers that this was a global phenomenon. Other parts of the world remained unaffected, even during the Lachamps event. It seems that a perfect storm might have been in play, where specific conditions over Australia left it more vulnerable to solar radiation. In terms of our global society, it's worth noting that these magnetic changes would take many lifetimes to complete, even at their fastest. This would be slow enough that we could come to terms with our new reality. If our satellites don't have enough shielding, we would have time to build some that were better protected. If solar radiation becomes a larger risk, we could remain indoors more. Sun cream might become more powerful, to mitigate the dangers of cancers, if not remove them entirely. And according to NASA, even if our field were to significantly weaken, it's not like we would be left without protection. Our atmosphere itself can catch radiation, meaning that we would remain safe from solar winds and cosmic radiation, at least to some degree. It would take far longer than 10,000 years for our atmosphere's ozone to be stripped away. But I would be surprised if there wasn't at least some turmoil, at least while we adjusted to living under a reduced magnetic field. Big changes to how a society operates are always painful. And this isn't entirely hypothetical. Did you know the Earth's magnetic field has been steadily weakening for the last 200 years? It would take another 1,300 years for it to vanish completely, so there's plenty of time for it to stop its current downward trend, and there's no reason to think this isn't just a temporary wobble. But on top of that, there is also the South Atlantic anomaly to consider, a section of the Earth's magnetic field that is already showing signs of significant weakening that covers most of the space around South America and the neighboring ocean. This zone might not influence life on the ground, but is dangerous enough that it has fried satellites and threatened astronauts. A Hubble telescope has to turn itself off every time it flies through it. Imagine that, but across the entire globe. That's what we might expect while the poles are reversing. Concerningly, the South Atlantic anomaly has been growing continuously since we started keeping track of it, possibly suggesting the approach of either another geomagnetic wobble like the Deschamps event, or that a full-blown reversal is already upon us. If it happens, it won't likely be something that ends civilization as we know it. But if the study about Australian megafauna is correct, it isn't going to be without impact either. Species could die. Humans will have to accommodate a very different, more hazardous space environment. It's interesting to learn about geomagnetic reversals and their potential impacts on the planet, but while we are not likely to see one happen in our lifetimes, for the generations of humanity after us, this might turn out to be a lot less hypothetical. They might be seeing it firsthand.
Given that this collapse has not occurred yet, and our magnetic field remains relatively healthy, you might think that solar weather does not have very much influence on life on Earth, except perhaps outside of the Sun's relative position to the Earth, as in Milankovitch cycles. However, you'd be wrong. What if I were to tell you that our neighboring star itself could affect your entire life? You might think that I was suddenly taking a turn away from astronomy and into astrology. Don't worry, I'm not.
While there are many people in the world who believe that you can learn things about your future by studying the position of stars and planets, it's not a position I tend to take on this channel. I'm more interested in the beauty of space and the mechanisms that explain why it is the way it is. But sometimes there is a grain of truth behind even the most surprising of stories. So allow me to put on my prophesying hat. While I'm no writer of horoscopes, I will predict that based on the current state of the sun,
as we get closer to 2025,
you might be more likely to experience bad health, less reliable technology, see warmer weather with fewer clouds, and possibly could be influenced in other surprising ways. How do I know? Because it turns out the sun, that giant ball of fire in our sky, is not just the place we get our energy from. Science is starting to show that its 11-year cycles might just be the metronome measuring out how life on our planet tick, tick, ticks.
Our fifth stop in our investigation of Earth cycles takes us off the Earth entirely.
I intend to show you exactly how the cycles of the sun are already influencing the course of your life. It's no surprise that the sun is influential to life on Earth. After all, in many respects, it is life's origin. Life on Earth needs energy to function, and the sun frequently provides that energy. Light for plants, plants for herbivores, herbivores for carnivores, all the way up the food chain. It's hard to find anything on Earth that could live without our sun. But beyond the gift of that life-sustaining energy, it's easy to think of the sun as fairly static. We see it rise and fall in the sky, but we rarely notice it undergoing any sort of change. This, however, is an illusion. The sun changes all the time. As science has advanced and we've been able to shield out the worst of the sun's glare, it became possible to study the sun's surface. As early as 1610, it became clear that the sun was a boiling, shifting sea of barely restrained plasma, which frequently wasn't restrained. In spite of the intense gravitational force holding it all together, the nuclear reactions taking place in its core are so hot, reaching 15 million degrees Celsius in its center, that plasma bubbles and bursts on its surface, erupting into solar flares that blaze in all directions. Sunspots, dark patches of the sun's surface that are filled with intense magnetic fields and can be between 1,600 and 160,000 kilometers across, form, drift, and vanish. Coronal mass ejections explode out of the sun's corona, the atmospheric zone above the sun that is strangely 200 times hotter than its surface. It's hard to find a place in the solar system that is as active as the sun. What many people do not realize is that that activity waxes and wanes. The sun operates on an 11-year cycle that alternates between a period of low activity, the solar minimum, to a much higher level, the solar maximum, and then back again. Sunspots, solar flares, and CMEs all become more common during the solar maximum. You are 50 times more likely to see a solar flare during solar maximum compared to the sun's minimum, and large CMEs go from happening once every few days to multiple times in a single day. This is known as the Schwabe cycle. Interestingly, this represents one half of a larger cycle known as the Hale cycle, which maps the changes in the sun's magnetic polarity. Once every Schwabe cycle, every 11 years, the sun's magnetic north pole and south poles swap places. When another Schwabe cycle occurs, the poles swap back. Tick, tick, tick. This constant rising and falling of solar energy levels thrums through our planetary system, rising and falling like a heartbeat. And surprisingly, even though we can't see it, we here on Earth move to its rhythm. We don't really understand why the sun goes through this cycle. It's clearly related to the magnetic processes that exist within the sun itself. Yet, although we have observed these cycles in action for the last 200 years and have seen evidence of their influence on the Earth over the last 10,000, we're still no closer to figuring out why the sun cycle has a length of that particular time period rather than any other. What force drives it? Lacking any other obvious answer, some scientists have tried to connect the orbital length of Jupiter, also about 11 years, to this cycle length, but this could easily be a coincidence. Although Jupiter represents 2.5 times the combined mass of all the other planets in the solar system, and definitely exerts some gravitational pull on the sun, its orbit cannot explain the variations, seemingly random, that the sun's cycle undergoes. Much of what goes on within the sun is a mystery to us, but its influence on Earth, that is much easier to see. It begins with the space around us. Space is more and more important to modern civilization, so it shouldn't be surprising that CMEs and solar storms streaming out from the sun more regularly would have an impact on the technology we have up there. Scientists are able to predict the arrival of a solar storm, known as a geomagnetic storm, by the time it arrives at Earth, days or even weeks in advance. This allows astronauts to go into safe shelters to hide themselves from harmful rises in radiation levels, and it also allows the delicate hardware on satellites to be powered down to prevent that hardware from being fried. This is important, as solar radiation can cause unexpected electrical currents to form in wiring, overloading systems that haven't gone into a safe standby mode. But there's another aspect to geomagnetic storms that you might not expect. All of that radiation has an impact on the atmosphere itself. It warms it, albeit just a little.
As the atmosphere warms, it expands, and this has an impact on our satellites. In space, there is no drag, so objects can orbit practically forever. Well, this isn't entirely true, and satellites in low Earth orbit do occasionally, about 4 times a year, need to expend fuel to correct their orbits, as there is still a tiny amount of atmosphere up there. But when a geomagnetic storm occurs, the atmosphere blossoms upwards, and low Earth orbit satellites have to maneuver every 2 to 3 weeks to keep from falling from the sudden friction. And this isn't always enough. In 1989, there was a geomagnetic storm that was so powerful, it knocked the NASA Solar Maximum mission out of the sky, as an increase in atmosphere suddenly slowed the satellite down. Ironically, the mission had been studying solar flares. This is not an isolated incident. NORAD, the Northern American Aerospace Defense Command, has to relocate hundreds of satellites after each geomagnetic storm, as they have been knocked out of their old orbits. Radiation can also influence our ionosphere, filling it with charged plasma. This can have a slight lensing effect on your GPS systems, reducing their accuracy from within a meter to over 10 meters. The next time you look on Google Maps and it thinks you might be a street across from where you are, a geomagnetic storm might be to blame. Our power grids brace themselves every 11 years for the uptick in these current-inducing events to keep themselves from being overloaded. Amateur radio enthusiasts and airline pilots find their high-frequency radio range dropping significantly as radio waves get deflected or even blocked completely by the more powerfully charged ionosphere. Although for such enthusiasts, this can have an unexpected side effect. By bouncing signals off the charged ionosphere, radio signals can sometimes be increased, and quite significantly, kind of like how skipping a pebble across the water can sometimes increase its range. Still, for the most part, as I predicted in my horoscope, this all adds up to some less reliable technology. The fact that the next solar maximum is expected to arrive soon, in 2025, makes me quite confident in my prophesying. There are some bright sides to this. As space weather becomes more turbulent, parts of the world such as Canada see a rise in the number of auroras dancing hypnotically across the sky. Aurora chasers report rises in sightings from a few times a year to as many as twice a month during the most energetic parts of the sun's 11-year cycle. So much for the sun's influence on space and our technology. You might think that that's the end of it. The sun cycle might influence machinery, but it's not going to make much difference on anything alive, right? If you think that, you'd be wrong. It's not for nothing that the rest of my horoscope mentioned poorer health. There's growing evidence that the sun cycles can even influence ecosystems and species themselves, including humans. Some of this is incidental. When the Schwabe cycle is at the solar minimum, the sun exerts less pressure through its solar winds, which means, ironically, that we get less protection from our heliosphere from cosmic radiation. This form of radiation is highly energetic, but fortunately rarely makes it through our atmosphere for that very reason, as it's likely to be absorbed or deflected by a passing air molecule. But reaching the atmosphere is all that's needed to produce an effect. There is a theory, although still far from certain, that this extra radiation could be creating nucleation sites in the atmosphere that seed extra clouds, influencing our weather. Even if that's not occurring, during solar maximum, the space weather hitting our atmosphere can raise global temperatures slightly. As my horoscope at the beginning predicted, a warming of the weather. Not by much, it should be said, less than half a degree, and the temperature always eventually returns to where it started, but it's enough that it's noticeable to species paying attention to temperature, for instance to decide when to start the mating season. Studies of birds have shown that on warmer years they tend to lay eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands went as far as to show that the laying times of blue tits were also affected by the number of sunspots occurring, which even the researchers found hard to explain.
It's not like birds can look at the sun to see how many sunspots there are. Nevertheless, a link seems to exist, according to the 5 nesting groups that were looked at. This isn't something that affects just blue tits, or even species like homing pigeons that are sensitive to magnetic fluctuations, who fly different routes depending on what time in the 11-year cycle it is. I'm talking about the last unmentioned point in my horoscope, bad health. There are numerous studies on how solar cycles might influence us. In 2011, a study spanning 2 decades of nearly 1/3 of women in Holland discovered a peak in 6 cervical pathologies that took place just after solar maximum, when the sun's radiation was hitting hardest. The study also checked 1 man during the same period, which admittedly is a much smaller number of candidates. Still, it was interesting to note that the man experienced slight elevations in oral temperature, pulse rate, blood pressure, and respiration rate that took place soon after solar maximum too. It's not just physical. There's even an influence on the rate of mental disorders. A study in 2006 looked at 237,000 clients in the main Medicaid database collected between 1995 and 2004. They found that, of all those clients, those born during higher energy chaotic cycles experienced an increased rate in mental disorders. If this is the case, then the cycle of the sun at the moment of your birth might just have influenced the course of your life. It's not quite star signs, but astrology might just be onto something, at least with one specific star. Ultimately, the science on this is still ongoing, and it should be stressed that any health impacts caused by these cycles are extremely minor. As one researcher put it, it took hundreds of thousands of patients to even notice that there was a health impact. The sun cycle should not prevent you from living your life. As of the release of this podcast, we're currently heading towards a solar maximum predicted to arrive in 2025. But for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might lead to a rise in creativity and adaptability. Perhaps it was during one such cycle, 80,000 years ago, that a human brain was mutated to give it abstract thought and consciousness. If so, if they gave us the means to perceive the universe, we have much to thank solar maximums for. We wouldn't be us without them.
The sun isn't the only astronomical body that influences us.
Much like the sun, the moon is an inescapable part of life on Earth. The moon has an immense impact on our planet. You likely have already heard how its cycles influence our wildlife, affect our climate, and create tides. We tend to imagine that the moon and the Earth's gravities cause them to circle each other in a relatively stable, synchronized harmony. But, as is so often the case, nature is not as simple as we imagine it. Instead, every 18.6 years, the moon's orbit undergoes a subtle revolution, a shift in its alignment between us and our sun that causes high tides to grow even higher, tipping us over the edge into dangerous flood territory.
We've arrived at our 6th cycle.
Its name is the Lunar Nodal Cycle, or the precession of lunar nodes. This complex name refers to a specific feature of the moon's orbit of the Earth. You likely know that every 29.5 days, the moon orbits the Earth. However, this orbit is not flat, or, to be more specific, there is a 5-degree difference between the angle of the moon's orbit and the ecliptic plane, the 2D plane on which the Earth orbits around the sun. For half of the month, the moon is slightly higher than the plane of the ecliptic. For the other half, it drops below it. Naturally, this means that there are 2 crossover points, or 2 nodes, an ascending node and a descending node, that mark the point where the moon goes from one side over to the other. And it is these nodes that move over the course of the 18.6-year cycle, slowly rotating around the planet in one complete revolution. The nodes themselves are what causes the problem. To understand why, let's recap what we know about tides. You may already be familiar with how the moon's gravity pulls the Earth's water towards it, causing a bulge in sea levels on the side closest to it that we call high tide. You likely also know that this happens on the side of the planet furthest away from the moon. Rather than being caused by gravity, this second bulge is caused by centrifugal forces, as the Earth and the moon's gravitational pull on each other causes them to behave like two dancers holding each other by the arms and spinning across the dance floor. While it's mostly the moon moving, due to the Earth being much more massive, the Earth is also swung around a little. The water behind it is thus trying to fling off into space through its raucous spinning, causing the second high tide. The Sun also has a role to play in tide formation, albeit to a lesser degree. It's a bigger mass, which would cause a greater pull if it were closer, but its further distance means that the Sun's effect is only 1/3 as big as the Moon. When the Moon and the Sun are aligned, we get extra large tides called spring tides. This happens 6 to 8 times a year. When not aligned, they partially cancel each other out, causing smaller tidal extremes known as neap tides. So now consider the influence of lunar nodes on this tidal tug-of-war. During spring tides, the pull of the Sun and the Moon working in unison causes the highest tides and the largest risk of floods. However, the Sun and the Moon are never more aligned than they are at a node. During the rest of each 9.3-year phase, they are not quite tugging in the same direction, so tides are more temperate. At a node, that's where things get more serious and risk of floods become highest. The last time this alignment occurred in September 2015, the UK and the US both issued major flood warnings to its citizens. In September itself, there were floods, albeit minor ones, but it was only when heavy rain combined with the strength of the lunar nodes a couple of months later that the real damage was inflicted. In the US, in October, South Carolina saw flash flooding that caused property damage and people having to be rescued by emergency services. At the end of December 2015, the UK was hit by some of the worst floods it had seen in a century. Combined with the power of Storm Desmond, flooding and storm damage caused an estimated £1.3 billion in damages. These floods can be highly damaging, but that in and of itself doesn't completely explain NASA's worry for the upcoming alignment in mid-2030. There is an extra element at play beyond the regular rhythm of this rising flood risk we have been seeing through the course of human history. Unfortunately, the next node's alignment with the Sun promises to be particularly devastating. The danger is that this phenomenon is combined with an already strained system, even more strained than it was in 2015. Over the last 100 years, we've seen steadily rising sea levels. When the next node aligns with the Sun in the mid-2030s, this will likely lead to a dramatic increase of floods on planet Earth. Worryingly, a new study led by NASA's Sea Level Change Science team predicts that almost all US mainland coastlines, Hawaii, and Guam will have a huge leap in flood numbers when this happens. Some predictions claim this node alignment could cause 4 times the amount of flooding from one decade to the next, which will damage infrastructure and change our coastlines around the world. This means human life will inevitably be affected by these floods, impacting shelter, clean water supplies, electricity, as well as the increased risk of waterborne disease outbreaks like hepatitis A and cholera. Plus, the receding floodwater can create stagnant pools of water where mosquitoes gather, which can spread other diseases like malaria. This has a knock-on effect on economic issues, as these natural events can make coastal life unaffordable, with increased cost of insurance on these homes, or an inability to find insurance at all, which could cause a reduction in asset value in the community. Consequently, this lunar nodal cycle will damage the quality of life in coastal communities, where infrastructure may not be rebuilt or adapted to this force of nature. It's not just bad for humans. Ilya Roshlin, a visiting professor at Rutgers University, analyzed that the peak of the lunar wobble where high tides are higher, can drown salt marshes. Salt marshes are a habitat for a range of species, such as invertebrates, and these floods can cause these creatures to drown, which means that other species like fish, seabirds, and others who rely on invertebrates to survive also suffer. And they aren't the only ones that rely on salt marshes, as salt marshes hold a multitude of marine life, which includes 75% of all fishery species. This means that the lunar wobble impacts the food chains of humans and animals, causing disturbances to their natural habitat and impacting their populations. While this all does seem fairly doom and gloom, it's interesting to note that not all ecosystems on the planet are negatively affected by flooding and high tides. Ecologist Neil Saint-Alain of Macquarie University analysed that the lunar nodal cycle impacts heavily on the expansion and contraction of mangrove canopy cover over most of the Australian continent. The analysis showed that the peaks of the lunar nodal cycle coincided with the cover of the mangrove canopy. It showed that when the lunar wobble is at its minimum phase, it causes the mangrove ecosystems to become very dry, which leads to thinner canopy cover. Yet, when lunar wobble is at its maximum phase, mangrove cover increases. Mangrove canopies are beneficial to Earth's environment as they are complex ecosystems that fight against climate change, protect wildlife, and shield coastlines. They can also absorb 4 times as much carbon dioxide than rainforests of the same size. Their growth is vital to the welfare of our planet, so it's not all downside. Still, it's clear that if we don't plan ahead, coastal cities and environments will face a serious crisis. The all-important question, then, is what can we do about it? One method is better protection. As mentioned previously, the protection and restoration of mangroves can act as a shield against flooding, as they can mitigate the vulnerability of communities on the coastlines. More specifically, mangroves can avert damage by decreasing the height and energy of waves as they pass through mangrove forests. The above-ground roots and branches diminish the height of the waves, and thus the waves lose energy, ultimately stopping the waves emerging onto the seabed and engulfing the sediments. The mangrove's roots and branches also reduce wind energy, which can stop the formation of waves. According to reports, densely packed mangroves can halve the height of a wave through just a 100-meter passage. For comparison, in an open forest where roots and branches are more sparse, it would take 500 meters for a wave to halve its height. So, preservation and reforestation of these mangroves, or plants with a similar capability, can become a great shield against upcoming floods. Another possible solution is to learn how to live with these flood-heavy conditions, working with nature rather than against it. For example, let's take a look at the flood defenses in the Netherlands, where 1/3 of the country is below sea level, and another third is at risk of flooding. They've built infrastructure that works with water and manages the rising sea levels. They do this by designing facilities like polders. Polders are bits of land below sea level that have been reasserted from a body of water. It's always fully or partially surrounded by an embankment to keep the water out that comes from either the sea or a river. These polders offer a network of drainage canals and pumps to manage water levels by disposing of excess water and running water back to the sea or river to make sure that the water doesn't run over land. Polders can be used to protect houses, farms, and factories, and thus are used a lot around the country. The Netherlands also built dams and utilized sand dunes to create ways to stay dry in their swampy land. This shows that there are ways in which we can observe nature and live alongside it. So, the bad news is, behind its ethereal beauty, our moon hides a power that, if just so combined, is set to overwhelm humanity's coastal settlements. However, there's always a bit of good news too, as knowledge is a power of its own. By understanding our plight, we can look for solutions, both among already existing ideas and ways forward that have yet to be discovered. If we are to endure what is coming, it's high time for us to use our innate creativity and drive to adapt and survive,
to work with our planet rather than against it. So here comes the moment of truth. How do all these natural cycles stack up to mankind's impact on our climate? These cycles in the position of the Earth, the ebb and flow of its winds, the churning of its core, and the far-reaching influence of its celestial neighbors all have an influence on the planet we live on. They move in rhythms that are predictable and solid, even if they sometimes take place over time spans that are so large that we don't always live to see them fully play out. Once we understand them, our understanding of our planet deepens. We are able to predict what's coming, whether it's floods, hurricanes, droughts, or years of plenty. But there is something happening to the Earth that we did not expect. Something that does not line up with any of these other cycles. Something that we may have to bear responsibility for. It's getting hot outside. Nowadays, it's difficult to turn on the news without hearing someone talking about global warming. Headlines are filled with references to rising temperature levels, fossil fuels, and encroaching danger. And the discussion around the subject has gotten as heated as the weather. This has been a topic I've been wary about weighing in on, simply because of how sensitive a subject it has become in recent times. I didn't want to simply create more noise. However, I do now think there is something worth adding to the discussion. After all, there is plenty we hear about the current temperature of the planet. What is often not talked about is the patterns of temperature change that existed in the past that contextualize that modern temperature. Are we really the hottest we've ever been? Scientists believe that in the last 100 years, the global temperature has been increasing. But how does this fit into wider patterns and trends? And how did they find any of this out? Well, to answer that question, we need to know, what did the temperature used to be? It's easy to find the current global temperature today. All you need is a thermometer, and you can go outside and take a reading. With enough readings taken at different locations around the globe, you can find an average temperature for the whole planet. Scientists have actually been doing this since 1850, meaning that our records on average global temperatures are fairly accurate since this date. However, mercury thermometers were only invented in 1714. So how do we know what the temperature was before these global readings started being taken? How do we know the temperature 1,000 years ago, or even 1,000,000 years ago, before humans were on the scene? Some of you may already know the answer, or at least a partial answer. Scientists can approximate global temperatures in the past through ice coring. Essentially, when snow falls, because it is powdery, it traps little bubbles of air where it lands. If this snow doesn't melt, but has more snowfall on it later, such as in a very cold place like a glacier, you can end up with layers of snow and ice trapped air bubbles going back for many, many years. It creates something similar to the rings on a tree. By collecting ice formed this way, scientists can take sections to a lab and melt it, releasing the air relating to specific years. They then can measure the different ratios of gases released from the air bubbles, which tells them the atmospheric composition at that time. And because we can test how much heat is retained by a gas when exposed to a constant temperature like the sun, for instance, CO2 retains more heat while oxygen retains less, with enough samples, scientists can calculate roughly what the global temperature was during that year. However, the oldest glaciers are only 1,000,000 or so years old. To get a good idea of the trends that govern global temperatures, we're going to have to go back much earlier than that. How do we know what the global temperature was over 1,000,000 years ago? The answer might surprise you. Clams. Actually, not clams, but something similar. A tiny single cellular organism no larger than a full stop called foraminifera. Like clams, these organisms produce shells around themselves, and these shells are slightly porous. Oxygen in particular is taken into the shell and trapped there, remaining in place even when the foraminifera dies. So, using a similar process to the ice cores,
If scientists can find shells of dead foraminifera from a particular year, they can release that air and work out from it the global temperature. This process is slightly different, as instead of air composition, scientists are looking at different oxygen isotopes, but basically it's a very similar process. Foraminifera are still around today, and first came onto the scene 500 million years ago, so they are instrumental in helping us get a clear picture of global temperatures during this much longer time period. But what is that picture? Well, unsurprisingly, the Earth's temperature has undergone significant changes over the last 500 million years, rising and falling repeatedly. At times it has faced temperature averages 14 degrees Celsius hotter than we have today, and at other times about -5 degrees Celsius lower. So we are not the hottest we have ever been. Then again, that's not surprising to anyone who knew that the surface of the Earth when it was just formed was mostly magma. But there have been a lot of fluctuations over the millions of years, a surprising number of them. Why are they happening? Scientists are not entirely sure, as there doesn't seem to be much of a pattern to them on the grandest scale, but they believe that some of these fluctuations are from the emergence of new life forms. For instance, the arrival of plants at around 450 million years before the present might explain why the temperature dropped then. They started absorbing atmospheric CO2 and turned it into oxygen, which retains less heat. Other changes could have been caused by plate tectonics and volcanic activity putting more CO2 into the air, and still other changes could have been caused by possible meteor impacts, like the one that wiped out the dinosaurs. However, this is not the full picture. Within the fluctuations are smaller fluctuations, rapid rises in global temperatures, followed by gradual dips, hundreds of them. It's hard to get your head around the sheer scope of the Earth's history, but each one of these dips represents entire ice ages. Ice ages are technically defined as any point in Earth's history where there is ice on the polar caps, something that is not always the case.
So technically, as I've mentioned previously, we are in an ice age right now.
However, although the general trend of the Earth's temperature at the moment is towards ice ages, we are in something known as an interglacial period, a span of many thousands of years where the Earth is temporarily warmer in between full ice ages. In the last full ice age, the polar caps reached the UK and parts of the US. Some of these peaks and valleys in global temperature are expected. They correspond with Milankovitch cycles, coming in every 23,000, 41,000, 100,000, 405,000, and 2,400,000 years. As they cool the planet, ice begins to form. But in the last 10,000 years, an unprecedented phenomenon has occurred. As I mentioned, we have risen out of an ice age and have entered an interglacial period, which for the last 10,000 years has been a fairly stable plateau of global temperature. This is consistent with the pattern you might expect, as Milankovitch cycles are slow things. All of human history, from the pyramids to the present day, can be found on this most recent plateau. Although humans existed before this point, they hadn't really got the hang of building any civilizations. Scientists have named this plateau where human history began the Holocene period. However, right at the end of this 10,000 year period, there is a sudden and rapid uptick in global temperatures. This is very unusual. This uptick represents a rise in the global temperature by 1 degree, which technically is still roughly on par with the interglacial period before our current one over 100,000 years ago. However, it is not the temperature change that is concerning about this uptick. It is how quickly it is rising. Unlike all the other changes I've talked about, which have taken place over hundreds of millions of years at the longest and thousands of years at the shortest, this rise took place in 100 years. 1 degree in just 100 years. This could have a big impact on the ecosystems on the planet as life struggles to adapt to changes this rapid. So, what could have caused this uptick? The answer cannot be Milankovitch cycles. As you have learned, These cycles take place on the scale of thousands of years at least, and millions at most. Milankovitch cycles are described as weak but consistent forces, like the trickle of a stream that eventually erodes a mountain. They do not create effects over such a small time frame as 100 years. Similarly, there has been no cataclysmic event such as the one that wiped out the dinosaurs, which might be our other explanation. That meteor was thought to be 10 kilometers wide and struck with a force of 21 to 921 billion Hiroshima A-bombs. About 75% of species died in the climate change that happened in its aftermath. If something like that had hit Earth since 1850, we would have noticed it.
None of our other cycles can account for temperature rises like this either. Or rather, they are already accounted for in the model. El Nino is understood well enough that we can tell this has nothing to do with it. This is not due to cycles of the sun, or the moon, or the Earth.
However, there is one factor that does explain this change in global temperatures: the activity of humans. It is not the first time that living organisms have had an impact on the global temperature. Remember, it is believed that some of the changes we see here are caused by the introduction of plant life absorbing CO2 and releasing oxygen. Similarly, back when life was still all single-celled organisms about 2.4 billion years ago, the arrival for the first time of cyanobacteria that could photosynthesize had a massive impact on the atmosphere. For the first time, an organism started putting oxygen into the atmosphere. This occurred at such a rate there was an event known as the Great Oxidation Event, which coincided with a significant drop in the global temperature. Some scientists believe the entire world almost froze entirely over, as there is evidence of glacial activity at the equator, a snowball Earth as it came to be known. What we learn from this is that the balance of global temperatures is very delicate. A single species that starts to change the atmospheric ratio of gases can have a massive impact, overloading the subtler effects of Milankovitch cycles. And since 1850, humans have definitely changed the way we have been interacting with the atmosphere. Unlike the previous roughly 10,000 years of human history, since 1760 and the Industrial Revolution, human activity has produced vast amounts of greenhouse gases as a waste product of industrialization and farming. In the last 4 decades, each decade has been the hottest decade on record since we started tracking global temperatures in 1850. CO2 levels are now at a global average of 410 parts per million, and methane at 1,866 parts per billion, which is higher than we have seen in the last 800,000 years, which means since before about 8 ice ages and interglacial periods between them. All this extra heat has an impact with its own feedback loop. Let's talk about wildfires. Earth has an awful lot more carbon than what exists in the atmosphere, but the majority of it is stored in either the ground, or in the deep oceans, or in biomass, which includes trees, phytoplankton, plants, and animals. Sadly, vegetation is drying out around the world because of drought and heat. This means it is more susceptible to fire. There is a biome on Earth called taiga or boreal, a region that stretches across Canada and Russia. It is the second largest biome on Earth after the oceans and consists mainly of coniferous forests. In 2014, a fire ripped across a section of boreal forest in Canada's Northwest Territories the size of Maryland, or 7 million acres. These fires alone released 94.3 teragrams of carbon into the atmosphere, about 103 million tons. This meant that this fire released half as much carbon back into the atmosphere as all the plants and trees in Canada typically absorb in an entire year. This creates something of a feedback loop. The more CO2 in the atmosphere,
the worse the frequency and severity of wildfires, and the more CO2 gets released. Biomass burning currently accounts for 30% of total carbon dioxide production across the world, but as the Arctic is warming faster than any region on Earth, these fires may increase in number and intensity. In 2016, 8.6 million acres burned in the Russian taiga. And on a direct level, let's not forget about the wildfires a few years back that happened in Greece, the US, and other places worldwide that have directly brought tragedy to people. The issue with trees burning is that they release a lot of the carbon they absorbed back into the atmosphere. That land will also take a while to regrow, as trees take decades to reach maturity. While these forests are regrowing, they are not at the same capacity they were. In 1988, a wildfire swept across much of Yellowstone National Park, damaging 36% of the park. Less than 30% of the burned area regained forest cover 20 years later. Let's talk about the Australian forest fire that took place from late 2019 to early 2020. It was big. On the 30th of December, smoke from the fires could already be seen from space. Their telltale brown hue separated them from the water vapor clouds alongside them. The fires burned throughout the night, and when the morning came, there was already a noticeable increase in their size. It was on this day that the military was deployed to some cut-off regions to assist the evacuation of trapped civilians. The smoke trail by then reached across the Pacific Ocean for at least 1,000 kilometers. Fires continued to burn through the night, and in the morning, it became clear that the wind had shifted, taking the smoke in a more easterly direction, completely blanketing neighbouring New Zealand. Sydney was also completely covered by smoke. This reduced visibility greatly, but also reduced the quality of the air for people breathing. Sydney had the worst air quality out of any city on Earth during this time. In the end, smoke from the fire was thousands of kilometers long. Wildfires are indeed a natural occurrence in Australia. However, none have been seen on this scale ever. But it's not just forest fires. The global cover of surface ice has been retreating consistently since 1950, something scientists do not believe to have happened for the last 2,000 years. As you will recall, this has a knock-on effect on Milankovitch cycles, as a planet with less surface ice does not reflect as much heat from the sun, so tends to get even hotter. Like pushing a cart down a hill, these changes have a certain amount of momentum to them. And sadly, rapid changes in global temperature tends to lead to species going extinct. It normally takes thousands of years for life to adapt to the conditions you might find during an ice age, woolly mammoths, to conditions today, elephants. Natural selection takes time to develop in a species the traits they need to thrive in a new environment. If species are not given this time, they either have to move to a new environment better suited to them, or they will die out. As the habitable zones begin to migrate towards the poles, some zones will vanish completely, while new, hot desert environments will be created that life in general is poorly adapted to. It's important to note that these events are not unstoppable. Global temperature change does have some momentum, but if we as humans find ways to stop changing the atmosphere's ratio, then in time, Milankovitch cycles will take over again and the rise will stop. That's why it's so important for governments to listen to reports by institutions like the IPCC, an international group of scientists funded by multiple governments tasked with finding out the realities of climate change, who in 2021 released their 6th assessment report explaining the physical science basis. In it, they stated that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. However, they also offered suggestions, namely the importance of halting or rapidly reducing CO2 emissions towards net zero,
as CO2 is the largest contributor towards climate change, followed by methane. They also recommended the development of carbon dioxide removal facilities to be established worldwide. Some of these are already in operation, such as Project Longship in Norway. Their aim is to take CO2 out of the atmosphere and bury it beneath the ground in depleted fossil fuel reservoirs. The IPCC says that actions like this, if widespread enough, will reduce global surface temperature and even reverse certain other processes like acidification of the oceans. Personally, I'm not super convinced by current carbon capture projects, but they do exist. But these efforts need to be done on a large-scale government level. Ultimately, my aim for the end of this podcast was to examine what global warming meant within the context of the Earth's wider history. From it, we can realize that it's not actually accurate to say that we're the hottest we've ever been, and I find that a really fascinating insight. However, that fact alone is not the reason some people think it is to not worry about the problem. Climate change is a process that usually takes millennia. I've realized the worrying part is not necessarily the change itself, but rather the speed at which it is happening. Some life forms might get left behind. And how will humanity cope? We don't know, as we haven't been around long enough to deal with the extremes of the past. While human activity has sped up certain elements, and while we can undo some of what has been done through our actions now, some things, like higher sea levels, will be with us for up to 1,000 years. According to the latest IPCC report, we are past the point of no return for 1.5 degrees Celsius, and will need to make rapid, fundamental changes to our society this decade to stop it going any further than that. This will be hard. There's no way we as a species will be able to achieve this hard path unless we can agree on the facts that underpin it though. Without the broader context of agreed upon data, it will forever be perfectly possible to arrive at a wide range of conclusions and different paths we should take. That is why, when it comes to any discussion, context is so important. By looking at the pattern of our planet's history, we can be sure that the current uptick in global temperatures is an induced event that doesn't match already existing patterns, and it perfectly coincides with human activity. Debate what you want to do with that information and the best path to take in light of it, but these are the facts, set in ice and the bones of organisms long dead. They will brook no argument. Ultimately, Earth cycles are all around us. They rise and fall, compounding with each other at times, and at others working in opposition. While their extremes can be destructive, by learning about them we can learn to live with them, and they certainly make sure that life on Earth is not boring. We as humans are now part of that process, although whether we will prove to be cyclical too remains to be seen. Perhaps our mastery of this planet will increase until these cycles are no match for us, and we will be able to set the weather and the temperature to whatever we want it to be in a given moment. But those days are a long way away. For now, it's important to understand the cycles of the planet and how we are influencing them, because whether we are ignorant of them or not, they will influence us. At least now, when someone offers you a polite conversation about how is the weather, you know enough to take it a little farther. Turn to them and say, "Too easy. I can tell you why is the weather." They may or may not appreciate that answer, and it might be the end of the conversation. But in my opinion, it's a fascinating topic to know about. Well, that's all we have time for today. I hope you've enjoyed listening to this slightly longer podcast on the cycles of the Earth. If you've enjoyed what you heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.